Hello everybody, this is again Dr. Sergey Sarkisov, and right now what I'm thinking about doing with us is showing you some of the latter concepts of Calculus 1, typically in a Calculus 1 class. If you even get to it, there's this idea, this technique of integration by parts. Before that, usually you learn integration, the U substitution method, right? And actually, some classes never touch upon integration by parts in Calculus 1 setting. So what I want to do is let me show you a few integration techniques and just some kind of topics, examples that are really cool, and look into this. So let's call it calculus. Calculus. Let's see if you can see that. Calculus 1. Some topics there. So let me show you specifically integration. And let me talk about, differentiation. There's something called the product rule, right? So let's remember, again, we're going to do a little bit more like on a sketch type of proof. Basically, I'm not going to go in detail of the analytical side of things. You know how calculus analysis part of it, right? What do? For all epsilon, there exists a delta, right? Epsilon greater than 0, very small, basically. There exists a delta such that if you're within the delta xy horizontally, then basically the limit exists if you can approach the function f of x minus epsilon less than, f of x minus the limit L is going to be, less than epsilon for any epsilon. So you get as close as you want to what the limit value is if you approach close enough horizontally, basically. That's just one of the initial elements of like a real analysis class, right? Or like an analytical side of calculus where you really want to show, hey, you know what, here's the formality behind everything that exists. The limit, then the derivative, right, which is the limit actually, and so on and so forth. But let me show you, let's kind of start from almost from scratch just to make sure we get everything down. So let's even prove the product rule, all right? Let me show you what I mean by that. So let's take two functions, f and g, right? And I'm not talking about chain rule, I'm talking about product rule. So product rule means we multiply f times g, right? So let's do derivative d dx. Okay? And I'm already assuming you know differentiation. You have most of the calculus 1 down, right? You've already done integration for some of it, right? So let's look at this. Derivative, just kind of refresh your memory, of the function f times g, okay, of x. And what that means is, it means the derivative of f of x times g of x, right? So basically this actually means d dx. And this is like, sometimes people say uv, right? F of x, g of x, uv, right? U of x, v of x. They use different letters. You've seen that a lot maybe. But anyway, look at this. So this means the derivative of f of x times, not composition, not a little open circle, but actually like a little dot, times, right? Multiply g of x. So this is product. And I want to show you the product rule. How do you differentiate this in any function f and any function g? And of course, there's a formality behind it that's continuous, it's differentiable, an interval, open interval, all that, right? We're not going to go into the depth of that, but watch. Let's use the definition of the derivative, right? So what is it? Limit as h goes to 0, right? This whole function, okay, but of x plus h, so you do f of x plus h, I'm going to kind of use that right there, times g of x plus h, okay, minus the function itself, of x, so f of x, g of x, okay, and all over, we're basically proving the product rule, is what we're doing right now, okay? So this is kind of like product rule. That's what we're doing. All over, and you know how the horizontal change would be, let me show you really quickly where this comes from. You would say the x plus h, that kind of, like how the slope basically of the tangent line at that point would be the y2 minus y1 over the x2 minus the x1. But you see that would just be an h left, right? So that's the idea. That's why you just put over h always. And you're like, why am I putting over h? It's because it's x plus h minus x. Okay. That's the idea. It's like a delta y over delta x in a little area vicinity where h goes to 0, meaning that they basically horizontally you get so small this way and so close to the function value that way that you're basically, if you look at it, let me show you what it looks like. Right here, here's some kind of function, and then you see that point right there? If you look at that little slope right there, the tangent line slope, and that would be basically that right there, that slope. This is delta y over delta x. This is delta y over delta x. Get it? So that's the idea. All right, anyway, you've seen this before. I'm assuming you know this already, rather extensively. So let's continue with this, and you've probably seen this proof already before too. But what happens is you have a limit as h goes to 0, right? Okay. And then here's a trick with this one you can do. It's kind of cool. Okay. Watch this. You say, you know what? I'm going to separate the fractions. So it's, what is it? F of x plus h, g of x plus h. So just copy it. Then, you know, I'm going to introduce something really cool just inside it for fun, like artificially, like almost like called a heuristic approach. So let me show you what I'm going to do. I'm going to say, you know what? I'm going to put minus f of this, almost the same thing, but I'm going to put this, g of x plus h. Okay? Well, okay. But if I do that, what happens? You can't just, it wasn't there, add it back, right? You can't just like randomly subtract the number without adding it, or some expression. Right, so we have this. So that's just like 0, minus plus the same thing. They didn't do anything to the value, but you know, it looks different a little bit, right? And then, of course, minus f of x times g of x. Okay? So let's keep this all over. That's just a h. The x is actually one away, right? And usually you don't even write those x's here. Okay? Now, look at this. Let's put brackets around this. Let's put brackets around that, and let's separate those. Okay? So, and I'm going to skip maybe a few steps here, but look. Limit as h goes to 0. Okay? And then let's look at that. And then, look, you know how it's like, let me show you a quick example. If you have 3 over 5 plus, let's do like 7 over 5. Everybody know you do 3 plus 5, right? I mean 3 plus 7 over 5, which is 10 over 5, right? Or you can do the other way around, 10 over 5. You can do 3 over 5 plus 7 over 5. As silly as it is that I'm doing that, it's a 2 actually, right? You can take this whole, you know, expression, and you can and this fraction, right? And you can break it down to this plus that, right? So in other words, you can do this over h plus that over h. That's what I was trying to show you there. That 3 plus 7 over 5 is the same thing as 3 over 5 plus 7 over 5, right? So it's kind of show my students here and there some kind of examples like that. So anyway, let's go ahead and do this one. So it's f of x plus h, g of x plus h, minus, I'm just going to copy that right there in the brackets, f of x, g of x plus h, okay, all over h, okay. And then I'm going to add that. By the way, remember how if everything works out in the limit of a plus b is limit of a plus limit of b. You basically can separate the summation. This is what is a linear thing going on here, right? So let's take this one with the limit of that, and then plus another limit as h goes to 0. Okay? And again, I'm skipping some formalities of like the differentiability, and maybe some of the locations where the function can be undefined or discontinuous, or we're assuming function's continuous. It's differentiable in the open interval. Okay, let's stick there. There are even nuances where even if that's not true, some of this still works. Okay, but let's just pretend it's the easy functions like continuous ones, the polynomials, the trigonometric. Okay. You know, I mean like sine, cosine, not like tangent, cotangent. Okay? Anyway, so here we go. And we have plus this, which is what? F of x, g of x plus h, minus f of x, g of x. Okay? All over what? H. Okay? And then, you know, I have brackets there, if you like. Just kind of make it look nicer. All right, now what? What happens is this, look, do you see we can factor anything out here? Well, this is in both of them, of these terms. F of x is in both of these terms, this one and that, right? So factor it out. Okay? So equals limit as h goes to 0. Okay? Let's factor out the g of x plus h. So you have f of x plus h minus f of x over h times g of x plus h, right? And you may see something really cool forming here. Okay? And then what happens? Plus, still trying to be kind of formal in some ways here. So in limit is what? H goes to 0. Now, take out the f of x. By the way, f of x doesn't even depend on the h, right? So you can later take it out, but let's keep it here for now. F of x times g of x plus h minus g of x over h. Okay? And what happens is, let me give you one extra step. I don't want to give you kind of just right away the answer. So basically it's going to be limit as what? H goes to 0. Okay, this, right, which is f of x plus h minus f of x. And somebody can already probably see what I'm trying to get at. Then that, right, and if you do like limit of a, b, it's limit of a times limit of b. Again, for the things that, you know, are really simple functions and continuous and differentiable, all that, right? So this times the limit as h goes to 0, what? G of x plus h. There's a reason to separate that for a second there, right? So this times this, and then plus what? Limit is what? H goes to 0. Don't forget the limit writing this. You can't just write the function without the limit part, right? But they will give you 0 points sometimes. Depends on the grader. Anyway, so here's this. Oh, by the way, I'm gonna get the eraser. You know, f of x, we can just take it out because it doesn't even depend on the h. So it's like a constant for this one, right? So f of x, and then times limit as h goes to 0, right? H doesn't change the f of x. It's independent of the h, right? That's so times this, like this, times g of x over h, and then so that's equal to, what is it equal to? Let's see. Now, what is this right here? This, everyone, is the definition of the derivative of just the function f, right? So this is f prime of x. This is, put an h in, which is 0, and for this, put it in, plug it in, like we call it. G of x plus 0 is g of x. Right. Cool, right? And then what happens? Plus. What is this? F of x. There's f of x. Just copy it. And what is this? That's the definition of the derivative of g of x. Kind of cool, right? That we came up upon it like this. And that's the product rule. Everyone? That's product rule. Sometimes people say derivative of uv is u prime v plus uv prime, or I usually say, you know, the derivative function is fg of x, f prime of x times g plus f of x g prime of x. And let me just show you some examples, so we're not, you know, just left stranded here without some kind of examples to kind of feel comfortable with this. So let's differentiate something here. Let's do d dx of maybe. And let's take two different functions. For example, a logarithmic and an algebraic. All right? How about this? What about x? ln of x. Let's do x squared ln of x. So what happens is, now look, we have two functions. One is squaring, one is taking the natural logarithm. Okay, ln is natural logarithm, ln of x. If you need up it. All right, and so if you forgot your natural logarithms, your logarithmic functions, this is basically log base e. The natural Euler's number e, okay? So this is log base e, okay, of the x, and then you have to kind of learn about logs or review that if you need to. But look, the derivative is, look, it's the derivative of the first function. You see the derivative of the first function. So what is derivative of x squared? Oh, 2x, right? We should know that, power rule. Copy, you see, just copy g of x. So copy ln x. Okay. And then plus, you see plus? Plus. Copy the first one, x squared. And then what do? What's the root of ln x? Oh, that's just 1 over x. Cool, right? So what is that? You see that's an x right there? So it's going to be, take an x out, right? What do you get? X times 2 ln x plus 1. Y'all see that? Cool, right? There we are. That's the derivative of x ln x. Yeah? All right. Well, that's how that works. So now, let's go to this idea of integration. That's kind of where I was going at. And so now, let me talk about something called integration by parts. Let's do a green color here, okay? All right. Integration by parts. So it's product rule, integration by parts. Integration by parts, I will not go that theoretical on this proof, but integration by parts, here's the idea. Let's see, y'all can see the green one. You can see it, right? You know what? I'll just do that. Let's Just going to make it kind of like visible. Okay, so what happens is, as you noticed, we already know dx of, let's do instead of f of x, g of x, let's call it u of x and v of x, u and v instead of f and g, right? So derivative of uv, and I'll keep it u v, okay, is equal to what? The derivative of the first one, call it u prime, right? Du dx, u prime. And then what? And you know what, u prime, you know what we're going to do? We're going to actually write u du dx. And again, this is a little bit informal of a proof, but we can do it. Du dx. That's f prime. Right there, down there. And then copy the next function, so times v. And then plus what? Copy the first one, u, and differentiate the next one, dv dx. Okay? See that? Now what happens? Now multiply everything by dx. It's linear. It's like delta x. A little, it's not 0. We multiply everything by it. Say it. We can do that. So what is that? D differential of uv is equal to what? This goes away. The dx's go away everywhere. So you get what? V du. I'm going to rewrite that order. And plus u dv, right? Okay. Right? And then what happens? Let's solve for that. Let's solve for that. And actually, you know what? Yeah, we can integrate both sides if you want first. So what happens is when you integrate everything, go basically anti-differentiate everything, this just becomes, I'll write it this way, but this becomes integral v du plus integral u dv. This is just uv. We're basically derivative of uv and we're anti-differentiating it. Okay, that's the idea, right? So uv equals what? This. V du minus or plus u dv. Now, if you solve for u dv, okay, let's solve for that. What happens? Integral of u dv equals uv minus this one, right? uv minus integral of v du. And that is right there, integration by parts. Okay? I'm going to go to like a red color, red marker. All right. So let me do an example with the red marker. All right. What if I asked you, this is really cool, kind of watch this. What about this? What's the integral of ln x? And put a little s value on it if you want, but we'll just pretend x is a positive number, okay? For now. So if you have to do that, what do you do? What's the integral of ln x? So basically, integral of ln x dx, right? That's integrand. I mean, that's the integral symbol, that's the integrand, that's the differential right there, right? It's a variable of integration. X. Okay, so what is that? How do you do that? It's an indefinite integral, right? We're going to have a plus a constant at the end. All right, where does that come from? And you're thinking, what do you do? There's a chain rule. I mean, there's the substitution. There's power rule and integration going backwards, right? What do? Where does ln come from? Derivative? I don't know. Do you know? Let me show you what happens. So if you think u substitution, let me show you what fails. Show you what fails for a second. So let's say u substitution. Somebody tells you, you know what? Try like ln. I don't know. Let u equal ln of x, for example, right? Okay. Well, all right. What's du? Now, derivative. So du would be, let me erase that, make it a little neater looking. It's a little low here. I'm trying to fit everything on this one side of the board so it's kind of visible. There's a whole other one, but it would be kind of hard on the screen, right? So du is equal to 1 over x dx. So if you even do that and you plug it all in, what happens? Look, it's like integral of, but x is going to come out, and you're going to get like x, see that? X, which is actually e to the, and then what? Du, x times u du, which is going to be what? What is x? Take e to the u, so it's going to be u e to the u du, and we didn't really get like anywhere. It's also tough, this one. So even u substitution fails. This is think about it, that's one of the strongest things you can do in integration because it's basically the backwards of the chain rule of differentiation, which is the strongest, differentiation technique we have of the basic fundamental ones, right? I mean, there's also like natural logarithmic differentiation, so like cool stuff I could show you another time. But anyway, what do you do with this? This fails. So u substitution, I'll come turn around a second. Nope. Sad face. Okay, it's not working. So what do? Integration by parts. Now, here's a trick, and not everyone agrees with me on this. Like mathematicians, there's a few different letters that use order, but there's one that I really, I feel is the best one, and that is liate, L-I-A-T-E. So let's do liate. Liate, and I'll tell you what that is. Liate, this is logarithmic, log, inverse, algebraic, trig, so like this, logarithmic, and this is exponentiation, See those letters? Log, inverse, algebra, trig, exponent, okay? So you see this UV thing? Because I didn't do any UV, I said let U equal, there's no UV, there's just a U, substitution, it's not working, right? So let's try integration by parts, here goes. This, from left to right, you do the U. And I'm looking at this U dV, right? I'm looking at that. Right now you may be like, what's going on? You may be not kind of new to this. If not, then you know already. But U dV. U, I will go from left to right on those letters. I'll show you what I mean by that. And V, I'll go right to left, dV. So dV goes this way. You pick something, okay? So let's look at our logarithm, okay? Integral of, I'm asking you just ln x dx. So integral of ln x dx. Now, equals what? Now, this is logarithmic. Is logarithmic on the left or on the right? It's on the left. Okay. So I'm going to let u be that. So I'm going to, right here, I'm going to say, you know what? I'm going to do u equal ln x. Okay. But then dv has to be the rest of it. And that's the algebraic. The dx, there's a 1 there. That's algebraic. So that's dv, turns out. So dv is going to be what? The remainder, 1, right? That's the dx. But that's algebraic. That's like, so algebraic is a 1. Okay, 1, it's a polynomial 1. X squared, x cubed, all that stuff, powers of x, even 1, it's x to the 0. It's considered usually algebraic. Okay? So this is algebra, and algebra is on the right, so it's going to be for this, and then logarithm is on the left, so it's going to be for this. If I flipped it around, it's not going to work. It's not going to be easy like that. So you got to get good. That's why the liate. I'll maybe do one more example to explain. But so look at this. Then you see this how it says like a du here and a v here. Okay. So look, what's du? Oh, we know that. What's du? Derivative of ln x, everyone is 1 over x. And of course put a dx. And what about dv? What's v then? Go backwards. How do you integrate 1 dx? Where does 1 come from? X, right? So v is equal to x. Yeah, you see that? If you dv, then it would be dx. It's kind of really trivial because 1 comes from x, right? All right. So now we're going to do this. You see this? U dv, u dv, u dv. It's equal to uv minus integral v du. So it should equal to uv, what's u? This one. V is this one. So ln x times the v. See? I'm doing this times that minus what? Integral of v. What's v? It's x. And what's du? Oh, 1 over x dx. All right, that's cool. This integral has become a lot easier, right? Because now look, all we do is, it's already going to have the answers x, ln x, and then minus an integral just of 1 right there. So minus just integral of dx. And that comes from what, everyone? Just a 1, just an x, right? So x ln x, that's a 1 there, 1 dx. So minus an x, and of course plus a constant. Don't forget the plus a constant. Okay, so let's just check. Is that really true, or am I making stuff up? Because it kind of looks like I'm making stuff up for some people, right? Let's differentiate this, and the c goes away. And is it really giving us back just ln? In other words, is the integral of ln x ln x minus x? Right here. That's the integral of ln. That's kind of cool. Almost like impossible to do, and then here it is. Pretty easy, right? If you know the trick. So let's try it. Let's check it out. dx of, you know, see that? Yeah. Of x ln x minus x, okay, is equal to what? Let's do product rule on that one and then minus a 1, right? Product rule on this one. What's the derivative of x? At a 1. Let's do this right now. Okay, so this is like on the left. So, again, the derivative of x is 1. Right? And copy ln x. This is product rule. Then plus, copy the x. What's derivative of ln x? 1 over x, right? And then minus a 1, derivative of x. And so equals to what? Ln x plus 1 minus 1 equals ln x indeed. So you see, this would be hard to guess or feel out that the integral, the backwards of ln x, the antiderivative of ln x, is x ln x minus x. I feel it's like hard to feel it, to just guess it. You know, like if you say x squared, oh, it comes from 1/3 x cubed. Because 1/3 x cubed gives you x squared when you differentiate it, right? X to the 5th, oh, 1/6 x to the 6th. Okay. E to the x from e to the x. E to the 3x from 1/3 e to the 3x. Like, we can feel that out. It's not that difficult to see some of those things. This one, as easy as it looks, it's just like, look, ln x dx is just one little thing. Can't do it unless we do integration by parts. That I did there, okay? And so, with that, let's do one more example. And then we'll call it class, you know? We'll call it a little end of the session here. So, let me erase some of the stuff here. Okay. Some calculus. Let me erase some of this. It's a good board here to actually erase it. I'll leave some of that stuff on the right. But basically, let's erase our product rule derivation, okay? It's kind of cool to see that sometimes, right? Because we always think sometimes, oh, v derivative is u prime v plus uv prime, and we're like, why is that, right? And like, we don't know sometimes, or we forget. Huh? Remember, the derivative is always the limit as h goes to 0, f of x plus h minus f of x over h. Okay? It's that kind of slope of the tangent line. That's one way to think about it. Okay? So let's check it out. Here's another example. Ready? I'm going to show you something really cool. All right, here we go. Let's try this. Let's do integral. I'm going to get a tough one, okay? Integral. Let's do x squared sine of x dx. Try to do something kind of a little different. Huh? I'm just going to go straight for it with this color here. And by the way, you know what? I'm going to erase some of this stuff here. Need some space. Blue one's not so happy to be erased. Anyway, so here goes. Y'all ready? All right, watch this. So let me erase this little thing, not confuse us. So our integral, call it I, or no, let's keep it like that for now, is this one, right? Now, let's go to the substitution. So I'm going to kind of do some stuff on the side as well. I'm going to try this. So we have, what is u? Now, what's algebra or trigonometry first? Oh, algebra's first. So I'm going to let u be the algebra stuff, and then the dv will be the trigonometry. So let's try this. U will be the x squared, and then dv, the remainder will be sine x dx. Okay. So let's go back. The derivative of this, du is what? 2x dx. And what's v? What's the integral of sine x? Go back. Go on antiderivative of this. Negative cosine, right? So negative cosine of x. All right? So then what happens? Well, remember what we do? We say uv, so it's a negative x squared cosine x. See that? Minus integral of this, right? So it's actually going to be minus a minus, so plus. Integral of cosine x is a minus minus, everyone. Follow me here. 2x dx. So we're going to get 2x cosine x dx. All right. Well, I don't know how to do that one really, not that easily at least. We'll see. What is that one? Are we just right away done? No. So then, I'm going to try this. I'm going to say, you know what? Look at this right here. No? This is going to be my integral I. So let's look at I just on the side. Integral I is equal to, let's just do what is x cosine x dx going to equal to, right? Let's check it out. So this one is equal to, let's do our own, what's it called? Integration by parts on this one by itself. So again, algebra, trigonometry, algebra goes first. So that would mean what? That would mean, let me show you, that I would let u equal to x. Now it's not x squared, it's x now, right? U equals x. And then what happens? And then the dv would be this other stuff. So dv would be the trigonometric cosine x dx. And then what is du? Du is just dx. And what's v? What's integral of a cosine? Sine, right? Antiderivative of cosine is sine. So then we plug it in here, and we say uv, so that's x sine x, minus integral of v du, sine x dx. And we know how to do this one now, right? We know what this one is. Right, everyone? This is actually going to equal to x sine x minus a what? That comes from a negative sine x comes from a cosine, right? So plus a cosine x. Yeah, plus a constant, but we'll do that later. Okay? So this one itself is that right there. So now our integral, get it? The one we want. Is going to equal to what? It's equal to negative x squared cosine x plus 2 of what? Of these. Get it? So you see how tricky this is, kind of like two integration of parts in one problem, right? And this is what? This is going to be x sine x. And it's easy to make a mistake here. We'll check to make sure there's no mistake. No? And then there's ultimately plus a constant here. So what the answer is, so far what we're getting, is we're getting negative x squared cosine x plus 2x sine x, right, plus 2 cosine x plus a constant. Okay? That's our answer. Honestly, I want to check this. I feel like kind of sketch. Kind of like maybe something's off, right? And it could be. Huh? Let's check it out. So let's do a little checking. Let me do like in blue. We don't do much blue here. Okay, let's differentiate this. The c goes to 0, and let's make sure from all this, will we get an x squared sine x? From all of this derivative, will we get x squared sine x? And then that's basically the check, right? Because if antiderivative of this integral, antiderivative of this thing is actually all that, well, if you differentiate it, will we get back x squared sine x? Let's check it out. So let's do product rule on this. There's a negative, right? So x squared goes to, so it's a negative 2x copy cosine x, right? And then there's a minus, so what is a copy of the negative x squared? And then what's the root of cosine? A negative sine. So plus, put a sign here. Okay. Then what is this one? Let's see, make sense everyone? This is that derivative. Let's differentiate. Okay. So we have, what is this? 2x cosine x. It's going to be plus, the x goes away, so 2. If I do 2x goes to 2, right? Sine x. And then if I copy the 2x, what is the root of sine x? It's cosine x, right? Cosine x. So I'm doing product rule. If you're familiar with product rule, you're not going to struggle with what I'm doing right now, okay? But I'll obviously have to do differentiation quite a bit beforehand, okay? And then what is cosine x? It's 2, so negative sine x, right? 2 minus 2 sine x, and plus a 0, constant. Let's see what happens. Anything cancel? Oh, goes away. Goes away. Indeed, we were right all along. Okay? So just want to let you know some examples of this one kind of ln. Oh, cool, we have to actually really do integration by parts to find just that little integral right there. You always wonder, like, what is the integral of ln x? I know derivative is 1 over x, and even that was tricky and hard enough to get there, from the differentiation part of the class. And now look, what about this one? It's kind of like, so let me tell you this. For fun, if you want to try something cool like that, try x cubed sine x. And it's going to be even more work, a few extra steps, and you'll see that. Otherwise, thanks for being here, everyone. And I'll end this session here, and we'll resume another time. All right, thank you.